Okay, this is the introduction to the social cost of carbon and integrated assessment models. This is following along from the welfare economics section of the course, so you should have watched the welfare econ videos, including marginal abatement costs, marginal damage functions, and three policies. So we're now, with the three policies, we learned that cap and trade programs and taxes were efficient policies and cost effective. Now the question is, what is the appropriate level of emissions, in this case CO2? We're going to be focusing on CO2. And then what is the appropriate price of emissions? And integrated assessment models are going to answer that question. They are going to help us find the social cost of carbon. The readings for this section of the course, we have a bunch from William Nordhaus. William Nordhaus is the developer of the integrated assessment models. He won a Nobel Prize for these things. His book, Warming the World, is a good place to look. There's a link to that here. I'll put that in the comment section of the video. There's some readings on Canvas, and then he also has several other books, one called Climate Casino is pretty good for an introduction to climate change policy, or the way economists think about climate change. So for this section of the class, we're moving on from studying the markets for electricity and oil and natural gas. We're now moving towards the externalities, addressing the externalities from energy markets, particularly pollution, and in this case, we'll be thinking about carbon pollution, CO2 emissions. So we're going to still try to do group presentations on the DICE model. The way it's going to work is you're going to work in groups somehow, figure out a way to talk to each other over WhatsApp or whatever program works best for your group. If you need help, you can contact me and we can figure out how to get you set up so you can work with your group. I've got several platforms I'm working with now that seem to work okay. Google Meet seems to work. The best way, I think, for you to do a group presentation is to do just what I'm doing now, is to create a PowerPoint, and then you can record a slideshow. You can record your voice over your PowerPoints. So I think what we should do is you can, within your group, designate who's going to present which slides, and then record your voice over the first 2 or 3 slides, let's say, and then the next person in the group will record their voice over the next 2 or 3 slides, and then so on and so forth, until you've recorded, your group has recorded an entire presentation, and then you send the PowerPoint on to the class. We all watch it, and we will all comment on it, and I'll give you a grade for it. So you're still going to be assigned to groups. I will assign the groups after I post these lectures, and it'll become more clear what the assignment is as we go along. We also will define the social cost of carbon in this section of the class. We will outline integrated assessment models. We will talk about the basics of the DICE model, which is an integrated assessment model. That's the one of the main ones used in policymaking. So we're actually going to use that model in Excel to estimate the social cost of carbon. We will estimate the social cost of carbon, and we'll talk about discount rates, and then we'll talk about key uncertainties in these models and how they affect the estimates. So the DICE model, it's an integrated assessment model. So what are integrated assessment models? They are large cost-benefit analyses. Your job as a group is to familiarize yourself with the DICE model. I will give it to you, and use it to ask questions such as what happens to emissions and global temperatures over time, economies, climate damages if the world does X. And then how sensitive are the results to changes in parameters or functions? So this thing is a gigantic model, and you are going to be responsible for playing around with it and seeing what happens to emissions up through 2100, 2200, and then if you adjust key parameters. You'll develop and test alternative scenarios. For example, what happens if the U.S. reduces emissions output faster than projected in the baseline model? Or what happens if the U.S. increases emissions output? How much should we, what are the damages from CO2 if under different scenarios? The group presentations. Okay, so here's the framework for your presentation. You want to ask the question, with respect to damages or whatever your topic is in the DICE model, what can be changed, and then, or what can be changed in the model to adjust how the damages affect the model outputs, for example. So you can outline the functions and the parameters for the class that can be changed in the model. I want you to provide information about what the user of the model needs to know in order to make informed decisions about changing those parameters or functions. So for example, why might you choose a discount rate of 3% over 6%? Or why might you choose a discount rate of 1%? Or why, if you're in the damages group, why might you have a quadratic damage function? So remember, in a couple of lectures ago, we looked at the marginal damage function. This model has a marginal damage function in it. Do you want it to be linear, or do you want it to be quadratic or exponentially increasing? And when you make those changes, how does that affect the model output? This will require you doing some independent research. So reading papers on your topic, getting paper recommendations from me, and then show us what happens to model outputs if you change your parameters. So you want to run the model with alternative sets of parameters, and then show us how that changes the social cost of carbon estimates. And then we'll end with a group discussion about each of the functions and the parameters that can be changed. So this will be done over Canvas discussions. How might you change them if you had unlimited modeling power and capabilities? What are the remaining uncertainties in the functions and the parameters that you've changed? How might the remaining uncertainties affect model output? And what else would you like to know about this topic? Here are the 4 groups, integrated assessment model groups. You'll be assigned to one of these 4. The first is discount rates. The point here is that you will be adjusting each of these parameters in the model and seeing how it affects the social cost of carbon. So you might be assigned to discount rates. The model considers future damages and benefits of avoiding damages, and those damages are placed into the present value terms via a discount rate. So how important is the discount rate in the model? And also, what is the appropriate discount rate for valuing intergenerational trade-offs? Intergenerational, we'll talk about that, yeah, so we'll talk about that in a bit. Group number 2, damage functions and catastrophic damages. How should we map climate change to economics? That's what damage functions do. Are the damage functions appropriately doing this? If not, how might we change them? Decarbonization. The model assumes economy-wide decarbonization as economies become wealthier. What is the correct rate of decarbonization? What do we mean by decarbonization? So right now we produce CO2 emissions when we produce energy. How quickly are we going to transition to a low carbon economy or zero carbon economy? That's the question for decarbonization. Climate sensitivity and radiative forcing. This is more along the lines of the kind of the physics of the model is how sensitive is the climate or temperature to additional CO2. So if we keep pumping CO2 into the atmosphere, how is the climate going to respond? And that's a parameter in this model that can be changed. And you have to do some research on the appropriate level of that parameter. All right, what's the economist's bottom line on global warming? The fundamental problem is that climate change is a global public good. It's an externality. It's a side effect or consequence of industrial or commercial activity that affects other parties without this being reflected in the cost of the goods or services involved. So everything we've studied so far, electricity production and consumption, oil production and consumption, natural gas production and consumption, those are all associated with pollution externalities. We have some local pollutants that we've talked about a bit, like SO2, NOx, mercury, and so forth. We saw at Rawhide they've done a fair amount to decrease the local pollutants. But one thing that they did not mention is when we were there, we could see a little bit of steam coming out of their, I don't know if you'd call it a smokestack, but an emission stack. The primary pollutant still entering the atmosphere from Rawhide is CO2. So we're going to be focusing on CO2 in this section of the class, the externality or the global externality, not a local externality. So we have local pollutants and global pollutants. We're going to be focusing on the global pollutants. It's a public good as well. It's something that is non-rival and non-excludable. And so, for example, if the U.S. reduces emissions, it cannot stop other countries from enjoying those benefits. So if we reduced all of our emissions, keeping the climate below a certain temperature increase, we could not stop other countries from enjoying the benefits of our reduction in emissions, and also keeping the climate below a certain temperature increase. So this leads to low participation and contribution. That's why we don't have a global climate agreement. The solution is that economic participants, millions of firms, billions of people, trillions of decisions need to face realistic carbon prices if their decisions are about consumption, investment, and innovation are to be correct. So that comes from Nordhaus. The key economic arguments are that to be effective, we need a market price of carbon emissions that reflects the social cost of emissions. So that should strike you as he's arguing for a tax. We need a market price of carbon, a tax, that reflects the social cost of emissions. To be efficient, the price must be universal and harmonized in every sector and country. So the tax needs to be global. We need to tax emissions at the same rate across the globe. There are caveats to that. We can talk about those at some point, but in general, that's what Nordhaus is saying. A major economic question remains: what is the appropriate price of carbon? This question is what we are addressing with integrated assessment models. U.S. climate change policy to date. For 40 years, all federal regulations were subject to cost-benefit analyses. The cost-benefit analysis is an analysis to weigh the benefits and costs of making a decision. For example, if the government wants to implement a new healthcare bill, they have to perform a cost-benefit analysis. So Obamacare, for example, we had to have a cost-benefit analysis to figure out what were the costs of passing the policy and what were the benefits. And then the Congress doesn't have to make their decision based on whether or not there's net benefits, but it helps them decide, hopefully. Until 2008, carbon was not included in the government-required cost-benefit analysis. In 2008, though, the Supreme Court decided carbon emissions damages had a non-zero value. In other words, producing CO2 emissions causes damages to current and future generations and is therefore regulatable. This came from a Supreme Court decision of Mass versus the EPA, in which the 12 states and several cities brought suit against the EPA to force the federal agency to regulate carbon emissions and other greenhouse gases. So what this does is it empowers or mandates the Environmental Protection Agency, the EPA, among other agencies and governing bodies to regulate carbon emissions. They now are required to regulate carbon emissions. And one purpose of the social cost of carbon is to allow agencies to incorporate the social benefits and costs of reducing carbon emissions into cost-benefit analyses. So if we want to, so the government's required to perform cost-benefit analyses for every policy they are planning to either pass or not pass. And if we want to include carbon in the costs of a policy or the benefits of a policy, we need to value it. And that's what we're doing here. That's what the social cost of carbon does, is it places a value on carbon emissions. So what's the social cost of carbon? It's a measure in dollars of the long-term damages done by a ton of carbon dioxide emissions in a given year. This dollar figure also represents the value of damages avoided for a small emissions reduction. So we could flip that on its head and say that it's the cost of damages of an additional ton or a marginal increase in carbon dioxide emissions, or it's the benefits of reducing carbon emissions by a ton. This includes changes in agricultural products, it includes sea level rise and human health and ecosystem costs. We'll go through the damages in more detail later on. If you look to the graph to the right on this slide, you see we have the private marginal cost and the social marginal costs. The social cost of carbon is the wedge between those two curves. So we're estimating that wedge with this model. We're estimating how high should the social cost of carbon be above the private, or how high should the social marginal cost curve be above the private marginal cost curve. How is it estimated? We use integrated assessment models to estimate them. And what are integrated assessment models? They combine the science of climate change, or the relationships between greenhouse gases and temperature and climate change and their impacts, with economics and policies addressing greenhouse gas emissions. And then there's feedbacks between the climate and the global economy. And we do this in a single modeling framework. So the model we will I'll give you includes a model of the global climate, includes a model of the global economy, and it links those two together, and the link is going to be climate damages from CO2. Why an integrated assessment model? Why are these models, why is a combined model useful for assessing climate change? Because greenhouse gas emissions affect climate change. Climate change affects economic production and economic welfare. Economic production and welfare affect greenhouse gas emissions. So it's cyclical. These models represent a continuous interaction between the economy, economic welfare, and climate systems. In other words, a policy that changes one of the above aspects changes all aspects and how they influence each other over time. The major goals of the integrated assessment models are to project trends in emissions, GDP, based on climate change and policy, assess the costs and benefits of climate policies, in other words, comparing the costs of abatement and carbon payments against the damages from different levels of emissions reductions, to estimate the carbon price required to achieve stated emissions reduction targets, and assess uncertainties and research priorities. How do they work? We're going to project future emissions based on socioeconomic GDP and population projections, combined with a key parameter CO2 over GDP. So that's the decarbonization rate. how much does CO2 go up as GDP goes up. So we're going to project future emissions based on the GDP and population projections out to 2100 or 2200 and see how that affects economic damages. We're going to translate emissions into changes in atmospheric greenhouse gas concentrations using carbon cycles built into the model. The atmospheric concentrations are going to be translated into changes in temperature based on the model's representation of the climate and the climate sensitivity parameter. And then changes in temperature are going to be translated into economic damages using a variety of damage estimates. We'll update the forecasted emission pathways based on relationships in the model and imposed policies, or carbon prices, and then transform the stream of future economic damages into a single value by discounting. So we're going to shock the model. We're going to forecast how the climate looks out to 2100 under baseline scenarios, and then we're going to shock the model with additional carbon and see how that affects GDP out through our our end date of the model, and then we're going to discount the damages back to current values. That's going to be our social cost of carbon. So here's the components of the integrated assessment model in a flow chart. In the top box, we will outline population, technology, production, consumption. This is going to be a production function that's going to be translated into emissions. Those emissions are going to be translated into atmospheric concentrations of CO2, global atmospheric concentrations. That's going to be translated into temperature changes and global climate change via radiative forcing. That's basically how the climate responds to different atmospheric concentrations of CO2. The temperature changes are going to be translated into socioeconomic impacts via damage functions, or in this flow chart, that's direct impacts on crops, forests, and ecosystems. So we need some damage functions. We need to figure out how temperature changes are mapped into real changes in crops and livelihoods, and in this case, we could be talking about pandemics, and then how do we actually place a value on those? And then all of that's connected. So the socioeconomic impacts or the damages are going to be then fed back into the forecasted population, technology, and production consumption, the first box, so that the model's closed, and that's done via a welfare function. Okay, next up, the basics of the DICE model.